Uh, Good morning. Am I audible? And is my screen visible?
Yes.
Okay, thank you. Sorry. Okay, so let us start. In the last class, we saw some examples of pthread and we learned the functions of pthread. So today's class will start with one or two examples of how we can convert a program from a serial program to a pthread program. What are the design considerations and how should we begin? Like two simple examples, and then we will move on to OpenMP. So the first example, which is a very simple example, which is where we are using a matrix X, and this matrix we are multiplying with a column vector, which is Y. So the output that you get should be a column vector again, right? Which will be this X into this A matrix into this X will give you a Y column matrix. Okay. So now how do we begin parallelizing this problem using pthreads? So the first thing is the serial program. This is how the serial program looks, right? Where we have two for loops, and two for loops. The first for loop uh, will we need two because we are having a matrix, and the we first we set the y value so that the y value is computed, and inside the second for loop we do the multiplication. So yeah, so what are your ideas, like how do we parallelize this problem using pthreads? Where do we begin? What should be like?
Can we break rows and column calculation differently?
Yes, we can look at that. So do we really need rows and columns calculation? Like as in what is the end result? End result is a one column vector, right? So the task of calculating the result, one column vector, that should be divided among threads, right? So what we can do is like, should we take the number of threads that your system can support, and based on what is the value of this y, what is the size of this column vector, we can directly divide the number of columns divided by the number of threads that we have. So each thread will expected to do the computation for one y value. Sorry, two y values in this case, because there are six elements in the vector, and we have three threads. Okay. The next would be how we will map each thread to the component it needs to calculate. So the first one, if you consider, we will need j is equal to 0, j is less than n, j plus plus will be able to calculate y of 0, which needs a of 0 of j into x of j, correct? And then this can be generalized for calculating y of I, where y of I is calculated as a of I of j into x of j summed over j is equal to 0 to j is equal to j less than n. This is clear how it is divided. Any other approach you think should be considered other than this? Anyone has any other ideas of how this division should be done?
Ma'am, why the plus sign is there before
This
equal
plus.
to? Yeah.
So, because as you can see here, this is y of I is equal to a of I 0 x 0 plus a of I of 1 x1 plus this is the formula, right? So we have to sum over j is equal to 0 to j is equal to n.
Okay.
Is it clear?
Yes.
How a matrix into vector multiplication is done. So the sum will be will start from j is equal to 0 to j is equal to n. We will have to add each element in that particular row and multiply it with our vector. Okay. So that's why we need this plus sign where every this will mean that y of I is equal to y of I plus this value. So the sum will keep on adding to this y of I, which will eventually give us what is the value of this yi. Okay. Hence, if we want to divide this work, we can. This is one approach where we divide the number of divide the size of our vector by the number of threads that we have, and each thread is supposed to take care of or calculate the y of a certain number of elements. Okay. So, uh, so what do you think now? What should be the scope of these variables for across the threads? All these x, y, a. What should be the scope?
It should be global
Yes. Why is it so?
because it's declared outside thread. Means it's in a process, defined in the process, and we are calculating inside the threads. That's definition of those variable is there in the process scope.
Yeah. Is it each here threads will need to access every element of row I of A, right? And every element of X. So we see that each thread needs to access every component of X, while each thread only needs to access its assigned row of A, right? In this
Yeah.
case. But at minimum, we expect X at least to be shared. Minimum X has to be shared amongst all the threads. Maybe A can be partially shared
Mhm.
if there is a way we can divide, right? But X has to be shared with all the threads. So, but we for simplicity or because it's fine here, we can also make A and Y shared. But this kind of violates our principle that we should only make variables global that needs to be global. But for simplicity, we can do that. And with other examples, we can also observe that this may not be the right choice. Okay. But why are we doing it? Because if they are all three of them are global, the main thread can easily initialize all of A by just reading the entries, whatever it gets, and then the product vector Y can be easily printed by the main thread because it is accessible to all the threads. Okay.
Ma'am,
So,
in
mm,
this context, the A thread, if you come on earlier slide,
yeah,
A
yes,
A matrix and the
yes,
X vector, both of them are going to be read by all the threads. They are not going to get modified per se. So it is safe to
yeah,
have them global, right?
yeah. In this example, it is fine to have them go.
Right, but Y is going to be modified as in yes, every thread is going to kind of put value in certain indexes of Y, but there
Mm-hmm.
could be a chance that if Y is shared across threads, as in let's say
Mm,
thread 0 is given the responsibility to compute Y of 0 and Y of 1, and mistakenly if thread 1
mm,
adds information in Y of 0 kind of a thing, as in
mm,
since it is accessible, it can kind of modify the index 0 as well, right?
mm-hmm.
Because of a programmer's mistake or something of that sort, then in that situation it wouldn't be wise to have Y as global that way, isn't it?
Yeah, I agree that if uh, if by mistake Y gets altered and we end up getting wrong results, having Y global also could be a issue. It would be better if we could divide, portion of Y amongst threads
Exactly.
somehow.
Okay.
Yeah,
Mhm. Hmm.
that also, yes, that also makes sense. Hmm.
Right. And again, if Y is global, since
Hmm.
it is accessible to all the threads, do we need to worry about threads, different threads modifying that value at one particular juncture? As in, do we need to put it in critical updation of Y
This
index?
so do
Would
you
we?
do you see a reason why we need critical section in this particular example?
In this example, it is not because every thread is given a certain responsibility, as in the problem is
Huh.
defined, right? We know that this thread is
Yes,
going to modify only this location. So here it is not.
I agree. Yeah. But
Uh,
in some other scenario,
mhm.
we might have to consider that critical section and look at it from other perspectives, like what else we can do to ensure that we do not have wrong results. But in this particular example, it is fine. We
Yeah,
can have it shared.
right.
Okay.
Until there is a programming mistake, one thread is not
Yes.
going
Yes.
to
Unless it is some,
modify.
yeah, yeah, some
Some else indexes in the output which are not owned by him. So
yeah,
probably
unless
we are
the
safe here. Hmm.
calculation of assignment of x in thread and y is wrong or uh, something goes wrong in the design phase that
Hmm.
it propagates in the final output. Otherwise, this program having them shared is fine because the
Okay.
threads are working on separate locations anyway. Okay.
Yeah. So rule of thumb would be if threads are modifying or if multiple threads are modifying exact same location, then we have to have a critical section so that we allow only one thread to modify that particular index at one point in time. But
Yes.
if they are given a responsibility of modifying different indexes, then it is okay
Mm.
not to have critical section.
Yes.
Yeah, and
And
in
what if
general,
in case?
hmm,
Yeah, yeah.
sorry, go on.
Continue. Then I'll continue. Then I'll ask the question. Yes, continue.
Yeah, and in case, sorry, I lost my point. Sorry, you let me remember that. You can ask your question. Sorry.
Okay. So, what do you think is the in this particular scenario, in case being a some conscious programmer and who wants to ensure that there is nothing wrong and wants to use critical section even in this scenario, let's say. Okay.
Mm-hmm.
So
Mm-hmm.
what do you think? What is the concern if that person uses a critical section here? What
Okay,
could happen?
critical
Means
section,
positive,
right?
negative. Yeah.
Right,
Yeah.
right. See, positive part would be we will not go wrong as far as updation of indexes is concerned, but the cost which we are going to pay is every critical section comes with a cost, and
Yes.
the performance penalty would be paid no matter whether there is going to be a race condition or not as soon as you put in the critical section. So it is wise not to have critical section when it is actually not needed.
Agreed. Agreed. That's
Yeah,
the point.
right.
So
In this
avoid.
particular example, it is actually not needed. And then
Yes.
programmers' mistakes are mistakes. We should not worry
Yeah.
about those situations.
Yes. Yes. I agree. So avoiding critical section, like use of critical sections, is very important. But at the same time, avoiding them as much as possible is also important from the perspective of gaining performance through parallelization.
Absolutely.
Because if we want anyway, the part of the code is to be done serially by most of the threads, then there is no point. From where are we going to achieve the parallelism that we need?
Absolutely. Absolutely. And just FYI, Ahmed's law,
Yeah.
Amdal's law talks about the serial
Hmm.
section. So
Hmm.
whatever
Hmm.
critical section we are going to make, that becomes
Yeah.
the serial component of the program. And as we saw in that particular law, the critical section, as in the serial component of parallel threads or parallel executions, is going to hurt us
Hmm.
very badly as far as the performance part is concerned.
Agreed. Agreed. Yes.
So we should absolutely ensure that we don't introduce a critical section when it is actually not needed. Rather, if we get into that situation, if we
Hmm.
consider even this example, dividing
Hmm.
sections of y based on threads is a better idea, and then accumulating them at the end would be wiser, so that we don't even
Yes.
give rise to performance problem introducing critical section, and then we don't have to worry about a thread having access to indexes, other indexes which he shouldn't update in a way.
Yes. I agree. Yeah.
Yeah,
Yes.
thanks.
And in OpenMP also today we'll see some features that are available to us, which with which we can avoid having critical sections and also ensure that we get correct results. There are some interesting features in OpenMP as well. Those we'll see today. Okay, moving on. So, yeah. So, what since we have considered that all the threads are global, okay. Uh, how do we are trying to convert this serial code to parallel pthread code, and pthread will need a pthread function, right, which will tell us what the thread has to be done. So now what should be the code in the pthread function? Okay, since we have made already the decision that we only have to write the code that each thread will use for deciding which components y it will compute to uh, So to simplify this code, let's assume that both m and n are evenly divisible by t. Okay, that t is the number of threads and m and n are the size of matrix. Okay, in our example, in the previous example, we considered that m is equal to 6 and t is equal to 3. This suggests that each thread will get m by t components. Okay, so what the thread 0 will get? It will get the first m by t. Okay, and thread 1 will get the next m by t, and so on. So this makes the formula for the components assigned to each thread q to be these two. The first one will have the thread number into m by t will be the first component, and thread number plus 1 m by t minus 1 will be the last component each thread should get. Is this clear how the components are divided? Components of y are divided amongst threads because we need this to finally design our pthread function. So if it's the previous, this is not clear, you can look at this code. Here, what are we doing? We first get the rank. We want the main function to supply the rank of threads. Based on the rank, we divide the pie amongst the threads. Now the first row which the thread should calculate should be my rank into what is the local M. Local M is the total size of the matrix divided by the thread count, how many threads we have. Okay? And the last row for this thread will be my rank plus 1 into local M minus 1. This will give you the last row. So you have to start from the first row till the last row and increment your I, and each thread will then compute its y of I using the same for loop. Okay, and since y of I is shared, we need not return it, we can return a null. Is this clear? Any doubts here? How we have now designed the pthread function for this matrix vector multiplication?
Yeah, where
Ma'am,
this
can you
Yeah,
please explain one more time component division?
okay. So now see the y we have whatever threads which is q is equal to, let's say 3 threads, and we have 0, 1, 2, 4, 5 and 6. Sorry, this, skip this. Okay, so the first thread q is equal to 0 will have the first now in this case particular m by t is equal to 6 by t, right, which is 2. Now the q, when q is equal to 0, that is the first thread, the first component will be 0 into m by t, which is the first
0.
element, 0.
Okay.
Okay. The last component for this will be 0 plus 1, 1 into, again, this will be 2, 2 minus 1, which is this. It will access these two. The t is equal to, or q is equal to 0. Right? Similarly, when q becomes 1, m by t is 2, 2 into 1. So it will start from the first element. This, sorry, second row. And the next will be 1 plus 1, 2. 2 into 2, 4. Minus 1 is 3. Okay, this is for q is equal to 3, m is equal to 6. If we increase this, when let's say m is equal to 12 and we have t is equal to 4. So m by t will be 3. Let's see what will happen for q is equal to the fourth thread. So fourth thread's first component will be 4 into 3.
Yes.
So it will be the, sorry, 4, q is equal to 4, where q is equal to 4 will be 3. Sorry, it will be, q will be 3 because we will start from 0 to 3. I'm sorry, I should have not written q is equal to 4. So q will become 3. So 4 into 3 will be 3 into 3. So it will start from the 9th element, and
Yeah.
its last element will be the 12th element. So
Yes.
11th element.
Okay.
Okay.
Got it.
So you understood how the division happens? Yeah.
Yeah, got it.
Yeah. So The same thing is done in the code. You calculate what should be the first element of each thread and what should be the last first row and last row, and accordingly it will do the computation for these rows for that particular thread. Okay, so you've understood how we can do vector, how can we do such division for any matrix into vector or vector plus vector kind of a scenario. Okay,
Yes.
so let us look at one more example before we then move on to OpenMP. This is for estimating the value of pi. Okay, so this is one of the formulas of estimating of pi. There are multiple formulas, but uh, you have to choose one to start, and so this is one that we chose. The reason for this is, as you can see, this has many factors, right, with which it needs to compute. And having many factors is useful in parallel computing. Why?
That helps us to divide the problem into different portions, which
Yes,
could be worked upon different threads.
yes. So this is important because we have enough portion which we can now look at and convert it or get it executed by multiple threads, and hence such a problem is ideal, or such a formula is ideal for when we are trying to parallelize the solution. Okay, so here what we are so in this code that you see here, this is a serial code. Now if you want to convert this code directly to a parallel code, what is the, do you find any place which is like uh, which could lead to any critical sections, or when where multiple threads might want to update a single memory location in this code?
Yes, it's a sum.
Yeah, the line number where sum is there, it is a critical section, and that we need to take care when we are trying to parallelize this code.
Yes.
So let us, yeah, let us first look at how we can parallelize this code without thinking about critical section yet. Okay, now here in this code you can see that again we have my first and my last, because we have to divide the total elements into different, factors which will be calculated by each thread individually. Okay, and so similar approach is needed here. So uh, and here, as you see, the formula is that every time the in the next line, first one is 1, the next is becomes negative, then positive, then negative, then positive, right? This is how we calculate the sum of the for getting the pi value. So this is important. This where it becomes positive and negative, the factor becomes is important, and hence for that you need this part in your code where you check if my first mod 2 is 0, that means it's even. If it's even, it's a positive factor. If it is odd, then it becomes a negative factor. This is very important. Then the critical section part where I you start with your first I and continue till your last I. You keep adding your or incrementing the count that you are doing, and keep switching between the factor positive and negative. Okay, and then you add this factor to your sum. Okay, is this clear? Any doubts here?
Ma'am, can you come on the earlier slide?
Yeah.
I'll just talk through for everybody's benefit over here.
Sure, sure, sure.
Okay, so if we, the task over here is to consider that bracket portion and see how we can divide that. Assuming value of n being very large, this will
Hmm.
give us huge amount of terms which needs to be computed. So
Yes.
idea is to kind of divide or consider this entire range, divide
Hmm.
it in multiple pieces, and then each thread will take up its piece in order to compute the value. So
Yes.
let's say there are 12 values and 4 threads, then
Hmm.
I'm taking very smaller numbers that way, but if we consider that number to be fairly high, let's say we have
Hmm.
1,000 components which are contributing and we have
Hmm.
4 threads, then initial 250 would be picked up by thread 0,
Hmm.
250 till 500 would be thread 1 and so forth.
Hmm.
And then
Yeah.
important parameter over here is if we have an even factor, then it needs to be added. If we have odd factor, it needs to be subtracted. That's the reason
Yes.
that factor element is important over here. So
Hmm.
for zeroth index, as in for zeroth index, it is going to be positive 1.0. For
Yes.
odd, sorry, for even it is going to be plus factor. For for even it is
Yeah.
going to
For
be plus
all.
I'm sorry. For
Yeah.
for even location, we want it to be +1. For odd
Hmm.
locations, we want it to be -1. So this is a simple loop, a sequential program, which is running from 0 till n. And at
Yeah.
each level, we initialize factor to +1. And then as for each increment, we are going to make it minus. So for every odd location, it will be minus. For every even location, it is going to be +1. And then sum
Yes.
is the final outcome which we want from this program, wherein we are accumulating things. That's the reason we have plus equal to, and then whatever
Yeah.
factor we compute for that particular program.
Yes.
Okay, can you get on to the next line?
Yeah.
Yeah, here on line number 6 and 7, we are
Hmm.
trying to compute from where I should start. So my first I is going to give us the index from where I need to start computing. My last I is going to give us the stopping point where I should stop.
Hmm.
And then it is important to have that factor as +1 or -1 based on whether it is even or odd. So those
Yeah.
that particular if else block is taking care of that. Once we take
Hmm.
care of that, if you see in the for loop, we are using starting point as my first I and ending point as my last I. So every thread is going to consider the range which is allocated to it. So 0 till let's say 249, 250
Hmm. Hmm.
to 499 kind of a thing. And then
Yeah.
factor is flipped between 1 and -1. So it
Yes.
is exactly identical to sequential program, but here we are ensuring that we divide the bigger problem into ranges and each thread works on a specific range.
Yes.
Okay, thanks.
Yeah. Okay. So moving on, let's say we implement this. Okay. And uh, so so now once we continue, okay, and execute this code, and we see that thread zero can add the first 10 elements, and uh, thread one will add the next 10 elements, and so on. We want now to like see how, as we increase the number of threads, how this program will execute. Okay, so if you see here, what is your observation in this particular example, in table, sorry, after we implemented this? This is the table, and even like the value of y, sorry, let me just give you the correct value of x. I think only then we will be able to understand. Okay, this is the correct value of x, pi. So as you can see, as we increase n, the estimate with one thread gets better, right? With each increase of factor in n, we get one correct digit when it comes to only using single thread. So with n is equal to 10 raised to 5, the result by single thread has 5 correct digits. Okay, with 10 is to 6, it has 6 correct digits, and so on. But what is peculiar about this? The result computed by two threads is getting worse,
Yep.
right? If we run this program several times with two threads and the same value of n, we might even see some different results compared to what we are getting using a single thread. So why is this happening? This is because it matters if multiple threads try to update a single shared variable. There could be issues which may not be, easily locatable, but are very critical. So, what exactly is happening here? For example, if you consider this example, where what you are trying to do is y is equal to compute of my rank. So here y is taking the rank, and next step x is getting updated with x is equal to x plus y. So thread 0 and thread 1 are trying to run the same code. When we are trying to do some updates in memory, as you might recall, what you have learned in computer architecture is that addition or updation of memory does not happen in one cycle. There is a process, and memory is a separate component and your ALU is a separate component. So whatever computation happens in your ALU, that is arithmetic logical unit, will has to be transferred from these results have to be transferred from your ALU back to your main memory, and that's where they get updated. So during this transfer, whatever extra cycles are needed, during that time, if some other modification happens to your thread or to your memory location, that may get missed. So for example, here, as you can see, what is happening? The main thread gets started. It will call compute. It will assign the value of y is equal to 1. During the same time, thread 1 starts in the next cycle. It will also compute 2. Then in the fourth line, as you can see here in this table, x is equal to 0 and y is equal to 1, which are transferred into your registers. After the data is in your register, you do the addition. Typically, in your architecture, you add 0 and 1, and this updates your value of x, right? But during the same cycle, the thread 1 has already copied x value from your main memory, and now it has x is equal to 0 into registers. So it will use the value x of x to be 0, and it will add 0 and 2. And now it will say that x is equal to 2. But what went wrong here is, although was updated, this was not reflected in for thread 1. Hence, this scenario is a typical scenario of what? What is this called? Anyone recollect? What do we call this? What happened here?
Race condition wherein same variable is kind of updated by two
Yes,
different threads.
yes. This is the classical case of race condition, where two threads are trying to update the same variable, and one end up updating it and the other one end up using a wrong value. Okay, so now this is where we have to introduce, in such scenarios, we need a critical section. You could use whatever you want to use, mutexes, conditional variables, semaphores, based on the application, but there is a need to use a critical section in such scenarios. So one approach other than critical section and mutexes and semaphores that we have already discussed in the last class, there is another very simple approach that we can do, which is busy waiting. So to avoid these conditions, threads need exclusive access to the shared memory region. So say thread 0 wants to execute the statement, you know, x is equal to x plus y, and it needs to make sure that thread 1 is not already executing the statement. So what we can do is, once thread 0 makes sure that it is not executing, it needs to provide some way for thread 1 to determine that thread 0 is executing the statement. So thread 1 should not attempt to start executing that statement until thread 0 is done. So finally, once thread 0 completes the execution of the statement, then it has to somehow inform the thread 1 that now I'm done, you please carry forward and do the computation. In that case, then thread 1 can safely start executing the statement. So one simple approach which does not need us to learn any new concept is using a simple flag variable. Flag should be a shared variable, and let's say we set it to 0 by the main thread. And if you add this code, the first one here, what is happening? Thread 1 finishes the assignment in line 1, okay, before thread 0. What happens when it reaches the while statement in the line 2? If you look at this while statement for a minute, you will see that it is doing something peculiar. That is, it is waiting, right? It is, so if the test flag is not equal to my rank, then thread 1 will just execute this step a second time. In fact, it will keep executing it till the test is false. When the test is false, thread 1 will go on and then execute the x is equal to x plus y. Since we are assuming that the main thread has initialized flag to 0, thread 1 won't proceed to the critical section in line 3 until thread 0 executes the statement flag plus plus. Okay. So when it's done, we see that it will execute a flag plus plus and thread 1 can finally enter the critical section and do the task. So the key here is thread 1 cannot enter the critical section until thread 0 has completed the execution of the task that it is supposed to compute. That is, done the task, do the flag plus plus, and then only the next statement will get executed. But what a catch here is, the very important part is these statements are to be executed exactly as they are written. This means that thread 1 cannot enter the critical section until thread 0 has completed it. So if you change the order of the statements, what will happen? Which is the other two codes? What will happen here?
Then the critical section is not safe. I mean,
Yeah. So yeah, so this concept of using flags or using while loops for waiting is called busy waiting. Okay, and this will work only if the order of instructions are not changed. And who has the power of changing the order of instructions other than the programmer who designs your code? Who can
Compiler,
check
I
the?
think it is
Yes, yes,
compiler.
yes. That is very important. That if you are using busy waiting, then you have to, and turn off the compiler optimizations. If compiler optimizations is on, it is possible that a compiler will make changes that will affect the correctness of this busy waiting. The reason is that compiler is unaware that the program is multi-threaded, so it does not know that the variables x and flag cannot be modified by another thread. So if our code is something like this too, it is run by just one thread, then the order of the statement, and x is equal to x plus y is not very important. But an optimizing compiler might therefore determine that the program would make better use of registers if the order of the statement is switched. But if in a multi-threaded scenario, this will defeat the purpose of busy wait loop. So simplest solution is turn the compiler optimizations off when we use busy waiting. And also, you know, what do you think is the issue with any other issue you see with busy waiting solution?
Ma'am, CPU time gets used without.
Yes, yes. So in case, let's say if thread 1 is execute the test over and over, and thread 0 is already delayed by for some reason, okay? Could be like operating system is trying to preempt it to run something else, something. So thread 1 will simply spin on the test, and this will eat up the CPU cycles. And this spinning is called as is spin lock, which can degrade the performance of your. So turning off compiler optimizations will also degrade the performance, and this spinning spin lock also will be very disastrous for your performance. So
Ma'am, this is a spin log, right?
yes, this is
Okay.
a spin lock. Yes.
Yeah,
So
last time I think we
yeah,
happened to bump into spin
it-
lock.
yeah. This is a spin. So hence, when therefore we need critical section, we have to take care of the critical section, but busy wait may not be the ideal option. But sometimes if you can use this because you don't have to do much here, just to add a while loop, and this is one way you can handle the you know such critical sections. Okay.
Ma'am, one thing here,
Hmm.
assuming there are four threads, okay, so
Yes.
0 to till 3 would be the distribution. If we
Yeah.
consider, let's say 0, 1, 2, those threads
Hmm.
have done their work. Now we are at thread 3.
Hmm.
So that thread is going to increase that flag value to 4. And we don't have a fourth thread, right?
Yeah.
We'll need
Yes.
to consider about that boundary condition here, isn't it?
Very important. Very important. And I was about to talk about the same,
Okay.
that uh, this condition, flag condition, is very important. And how can you create this flag condition such that you are not stuck in the loop, and you can come out of the loop. So for let's go back to our estimating of pi, value of pi. So what have we done here? What do you
Yeah.
think is the solution here? What did we do?
Yeah, line number 17 is the solution wherein we are
Yes,
ensuring that we remain in the thread boundary 0 till
yes,
3. In
0 to 3, so that we remain in the thread boundary, and we are not there is no we're not stuck waiting for this flag to be reset, and threads are not lost waiting.
Ma'am, this factor should be a shared variable, right, across thread?
Um,
if we want to apply the busy bit or it's something different.
So, uh, factor is if we want to do
No, no, so,
busy
no,
bit.
not factor.
No, no,
I
no,
mean
no.
this
Flag,
flag.
flag,
Sorry,
flag,
sorry,
flag, flag,
flag.
flag. So flag is, yes, flag is a, it's a shared variable, right?
For
Flag
global.
is not, it's a global one. Yeah.
Okay.
And when we make flag as global variable, as in it would be accessible by all the threads, uh, can you please explain why we won't get into race condition for flag in this situation?
Because updation of flag will be access to one thread at a time. Because here, once, see, only one thread will enter this section, and updation can be done only by one thread at a time.
Okay, okay. Until that my rank and flag matches, I will
Yeah.
not execute it. So
Yes.
that way we are forcing that
Hmm.
only one thread is given opportunity to go ahead and execute sum and flag.
Yes.
Those two instructions in a way.
Yes.
And until that flag value is incremented,
Hmm.
none of the other thread is going to see a different value for flag, and it will just keep on waiting, as in spin lock, what you explained. It will
Yes.
keep on spinning on that while loop indefinitely
Hmm.
until it sees the right flag value.
Yes.
Ma'am, is there a danger of deadlocks if we kind of get into such approach? Because there could
Mm,
be inherent things, right?
depending on
Based on
depending
prop.
on the
Hmm,
application, yes,
hmm.
this
As in,
can lead
if
to a deadlock.
correct,
Yeah.
correct. This may not be elegant solution. It is just one of the way to deal with
One
things,
of the
is what you're
ways,
trying.
yes, yes, the most basic way before we tried out things that we tried out in the last, like mutexes, semaphores, conditional variables. This is the without introducing anything new, you can do
Hmm,
this using just a flag.
correct. And
Because
this would.
see,
Hmm,
if we add like uh, if you use this uh, for what is seen is, let's say when n is equal to 108, the serial sum is consistently faster than the parallel sum. So for a system of dual core, okay, the
mhm,
elapsed time for the sum by using two threads is about 19.5 seconds,
mhm.
whereas the time for serial sum is around 2.8 seconds.
That's a huge difference, isn't it, ma'am?
Yes, yes, there is.
Why would we write a parallel program in that case?
Yeah, yes, I agree. There is overhead associated with starting up and joining the threads.
Hmm,
There is also which you can get by just checking what is the overhead. You can use the thread function, this same thread function, and ask it to do nothing. Just return the null, and you can get what is the overhead that this thread function creates. Okay,
mhm.
but apart from that, we see that the overhead is for this on the dual core system was around 0.3 milliseconds. Okay, which is very less. That means the slowdown is not due to the thread overhead, but
Mhm.
it is because of the busy waiting function.
Okay, the spin lock.
So
While
spin lock.
statement in this particular case.
Yes, yes,
Ma'am,
yes.
could you please explain, as in the situation wherein which particular style should be used? As in spin lock is one of the style of having critical section. Then we have locks, conditional statement, the way one which we saw last time. Then semaphore. Like in which
Yeah.
situation, which locking style is should be chosen, is preferred. Is there any slide where you are trying to cover that particular portion? Because that's one of the most important part, right? We need to ensure that we pick up the right style. As in here, spin lock is not the right approach. As in it is going to give us the right result, yes, but it is going to make the threads wait for much longer. So is there any
Yes.
better way of doing exact same thing, getting the right sum, and even the better performant way? So are you planning to
Yeah.
cover that
So
differences
yes. So
between
next
those
in
four?
the next
Mhm,
uh yeah. So see okay. So the yeah. So as we have seen, we have multiple techniques, right? And
mhm,
each technique has its uh, advantage, disadvantage, as well as specific application. Why you
right.
need what? Okay.
Mhm,
So because see, spin locks is can be used when you need some very you know low latency synchronization is there. That is, threads will be only waiting for a very short period. Then you can use spin locks where the waiting period is very small.
Okay, when
Okay,
you say waiting period, you mean the execution
while
time
loop.
required for,
Hmm.
but see,
While.
while loop
Hmm.
is going to make a thread spin at that particular line, as in every thread will stop at 15
Yeah.
except the one
Yeah.
which is going to compute sum and flag, right?
Yes.
So
So the
execution time of those two instructions is going to decide how much time the other threads are going to stay on while statement, isn't it?
yeah.
Okay, okay,
So if it is very small, then only you should go for spin locks. If it is going to be longer, then spin locks is a very bad idea. Okay.
okay. Mhm,
Then see condition variables is where you need to signal between threads or wait for some specific condition to occur. And that's where we saw how it is used in producer consumer. Semaphores can be used when you have some limited number of slots or some limited number of instances which you can compute or get the information using some count, such as if you want to limit the number of threads accessing a resource, the way we have seen in the producer consumer problem. That's where the semaphores will come into picture. Mutexes you can use wherever you want when there are shared resources and you want to control the simultaneous access. But along with mutexes, you have to write some extra instructions for using them for conditional or semaphore kind of scenarios. Okay, but
mhm,
read light lock specifically, those can be used when you have a shared resource that's mostly read and occasionally written. There you can use some read write locks. Okay, which is, for example, a database that is frequently queried but infrequently updated. In those case, you can use read-write locks.
okay.
Then the when you're trying to choose the synchronization techniques, you should consider factors like what is the performance requirement. That is, uh, because different techniques have varying overheads. So, what is the requirement for your particular application? The
Mhm,
next could be that what is the complexity? Like some techniques are more complex to implement correctly. What will the complexity of implementation defeat the purpose of using the technique? That also is a very important criteria. And what is the specific problem requirement? So, what is the special need of that problem? Whether it is can be taken care of with conditions or can it be taken care of with semaphores or only a simple mutex will do the job. So
mhm, okay.
these are multiple factors you have to consider. Okay,
Yeah,
so moving
yeah.
on.
Were you,
Yeah,
ma'am, were you able to locate the problem which we had last time, as in the producer time was increased, sorry, reduced and consumer time was increased, and
yeah,
still we
I
were
think
not.
I yeah, I think I fixed the solution, but I did not upload the pthread codes. I realized that I'll upload those post class today. I have
Okay,
fixed that, and yeah, I'll upload those post class all the pthread codes,
okay. Just put in the old and new
including that one.
version so that, yeah,
Yeah,
so
both
that we
are
can
there. Both
differentiate.
are there.
Okay,
Yeah,
okay,
both are.
okay.
Okay, uh, so we have seen that busy waiting is generally not an ideal solution, because it will limit the access to critical section. And the two better solutions in this scenario would be obviously using mutexes or using semaphores. Okay. Uh, and we've seen mutex is basically mutual exclusion, and it's a special type of variable that when we use with a couple of special functions can be used to restrict access to a critical section. So with this, in this particular example, mutex is using, or guaranteeing that one thread excludes all other threads while it is trying to execute the critical section and summing it, right? So is this example clear? So what is happening here is first
Ma'am,
thread, which we'll call, yeah,
it's
yes,
clear the how are we using the mutex here. But
yeah,
here
yeah.
also we are putting other thread in a wait cycle. Like if one thread is working in the critical section, other thread is waiting. Means it's going to lose some cycle also here also.
Here also, yes, some cycles will get lost, but we'll see the difference between the two. What is it? But I have put a table in the next slide, so I'll go to that. Hmm?
Okay.
That's
Yeah,
common, right? In critical section, it has to wait. Only one can allow,
yeah.
so other have to wait.
We
That's the
can't
Bible.
help it. Yes, and we have to avoid as many critical sections as possible. So avoiding them is, if possible, because for some application we just can't help. We need critical sections.
Right. Just one difference over here is once see if you can come on the earlier slide map, I'll just talk
Yeah.
through my understanding.
Hmm.
See here we are making use of spin lock as ma'am explained. On line number 15, we have a while statement which will ensure that I will stop at that statement until my flag value matches my rank.
Hmm.
Now while statement itself is something which needs to be executed. So when operating system as in scheduling happens, scheduler will need to go to every thread as in all of us as in time slicing mechanism is used in order to give a slot to each thread for execution. While is a legitimate statement which needs to be executed. So whenever a thread gets its slot, it will execute that while statement. So operating system or scheduler has to give a slot to that thread, and that thread is going to just execute that while statement and remain there. And then all the four threads which will keep on getting their own time slice, all of them will do some useful work, as in sum and flag execution would be a useful work, but rest all are going to execute that while statement. Now if we go with this particular mechanism, operating system doesn't have a way to identify whether given thread is going to do something useful or not, because for operating system it doesn't matter whether it is a while statement which it needs to execute or a sum statement which it needs to execute. Every statement is going to be a legitimate statement, so it is going to give a slot to thread. Let's say when thread 0 is in context, it will go ahead and execute sum and flag related statements, which is line number 16 and 17 in this example, while other threads are going to execute line number 15, which is a while statement. So operating system will need to allocate time slice to each thread in this particular
Hmm.
example. As against that, if we move on next slide, when we make use of online number 18, we have a pthread mutex lock. So mutex is a mechanism which operating system understands. So operating system
Yeah.
will ensure that the time slices are given in more intelligent way, as an operating system now knows that there is a mutex concept, so it will look at mutex, and based on who is holding that mutex, it will give cycles to that particular thread, and other threads will be put into a wait queue until that mutex value changes, as in until that thread gets the mutex, it will not be pulled out from wait queue and into execution queue. That way operating system does a better job, and it gives a priority, or it gives more cycles to the thread which is actually going to execute line number 19 and 20 instead of the threads which are just going to execute that while loop in earlier scenario. So this way, operating system does a better job of giving time slices to important thread, and very little time is taken up in order to put a thread from execution to queue to waiting queue, taking from waiting queue onto execution queue. So operating system does a better job, and that's the reason this is better approach as against the while loop approach which we saw in the earlier slide. Is that understanding fair, ma'am?
Yes. So yeah. So yes, I agree. So what happens, as you mentioned, that with mutexes, the you know when a thread tries to lock a mutex which is already used, the thread is blocked until the mutex is unlocked. Okay. So OS scheduler will remove the blocked thread from CPU and allow other threads to run. But with spin lock, that's not the case. When the thread tries to lock a spin lock that's already held, it spins in a loop and it keeps checking if the lock becomes free. So the thread remains active on the CPU, which leads to consuming more cycles. Correct?
Yep.
The,
Yep.
yeah. Hmm? So,
So
uh,
are you
in,
does it
so
mean, ma'am, pthread mutex lock is um, we implemented the same like previous locking mechanism, global flag mechanism in a better way inside, so that we can avoid this CPU cycle wasting. It's something like the implementation of this function is uh, written in a way that OS can takes care of the CPU cycle and
hmm,
makes sure that it will not waste the cycle for waiting threads.
yeah, see, with mutexes, it involves context switching. Okay,
Okay.
so it allows switching between threads. With spin lock, there is no context switching.
Okay.
Okay, but there is this is positive as well as negative because with context switching, there is overhead of context switching, which is part of mutexes. But with spin lock, that overhead is missing. But it is wasting CPU cycles because if you are holding the lock for a long time, which the amount of time taken for using this lock is not comparable to the time or overhead that is used that is needed in context switching, then the spin lock become a very bad idea. So if you ask me in terms of performance, what should be preferred? You prefer a mutex for long critical sections and spin locks if for very short critical sections. Is it clear?
Yes, ma'am.
Yeah. Ma'am, could you please explain why switching is going to happen more in mutex as in?
Yeah. So in mutex, what is happening is
Mhm.
OS. Uh, so what happens is when a thread tries to block on mutex, which is already held, the thread will be blocked, right? It will be put
Correct.
to sleep.
Correct.
The OS will remove the blocked thread from the CPU and allow other threads to run during the same time.
Correct.
Hmm? Whereas
Y-
in
mhm.
spin lock, what happens is when there is a thread which is held, it will keep checking if the lock is free or not. So the thread will continue to remain active in CPU. It is not removed or it is not put to sleep. It will continue consuming the cycles until it gets the lock. Right?
Correct, but context switching will definitely happen even there, right? Because a time slice is the portion based on which the context is going to switch.
No, no. Here the thread is executing the while loop. It is executing something.
Correct, but let's
Why
say
will you
thread
switch?
zero,
Why do you
right?
do context switch?
Thread zero gets a slot. Once thread
Hmm.
zero slot is complete, thread one comes into context. So there will be a
Hmm.
switching from thread zero to thread one, right? That's the context which
No,
we are talking
no,
about,
no,
right?
no, 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 no. No. Context switching, I think you're misunderstanding
Threads can
something.
run parallel, right?
See, there
No
is
need to context.
one core.
Mhm,
This is a core pay, one core is there, and on that core,
mhm,
multiple threads are executing. By
mhm,
dividing time, that is context switching. One thread is executed, then some other thread is executed, and some other thread is executed. Whereas that will not be the case here. That core will be kept occupied by the thread which is waiting. It will not be given to any other thread to execute, because the spin lock will ensure that you are doing something, that you are just executing that instruction again and again and again.
mhm.
So that the any other thread cannot access this core and do some useful execution. That cannot happen.
Okay. That does mean all the threads remain in the execution queue, is what
Yes,
you're trying to
yes,
comment. Okay.
yes, yes, yes.
Okay. And,
Because
what?
they are
Hmm,
active. They are not put to sleep.
correct, correct,
The
correct.
way
But
we do it in mutex. Yeah.
right. But now once if we consider time slice, if thread zero is
Hmm,
given time slice, when the time
hmm,
slice is over, thread zero will go off the execution and thread one will come into context, right? So that
hmm.
would be that is termed as context switching, right?
Yes. So yes. So when the when thread zero, slips as in steps aside and lets the code be used by some other thread,
Hmm.
that is context switching.
Right. Now that context switching is going to happen in case of spin lock also, right?
No, because in
No?
spin
Okay.
lock, a thread is continuously executing. So okay, so this is code zero. Okay,
Hmm.
code zero.
Okay, you're talking about multi-core. Okay, I'm sorry. I
Yes.
thought we are talking about single core. Okay,
No, no,
that's
no.
the reason I got confused. Okay, so here, okay, I see what you're trying to comment. So the point which you're
Hmm,
trying to make is assuming there are four cores
hmm,
on the system and we have four
hmm,
different threads, then every
hmm,
thread will get associated with that specific core and it will
hmm.
remain in the business. It will not be taken
Huh.
out at all in case of spin
Yes.
lock. That's the
Yes.
reason we save on to context switching time.
Hmm,
But if we consider mutex based locking mechanism
hmm.
in the same situation,
Yeah.
one thread is given to core 0 and let's say
Hmm,
T1, T2, T3 are the remaining three threads which look at the
hmm,
lock and get into sleep state. So they
hmm.
don't even get executed on their respective cores that way, right? So there is an
Yeah,
opportunity that
yeah. They can switch. Hmm.
those cores will be executed or those cores will do some useful work for some else
Yes.
purpose.
Yes. Yes.
So even then, we are doing a better job with mutex as against the spin lock, isn't it?
Yes. But see, there, if the waiting is for a very short period, there is extra overhead of context switching as well, right? Removing
I
the
see.
thread
I see.
from and making it slip and starting another thread. So that gets avoided with with spin locks.
Oh,
So
yep.
if
Yep. Agreed.
the amount of waiting is very less than the
Hmm.
overhead that you can cause because of context switching, then you can use Texas.
Right. Operating system needs to put a thread to sleep,
Yes.
figure out another thread which needs to do a job, and then if that sleep time is too less, then it would just be context switching between multiple threads, and we will lose good
Yeah.
amount of time in doing context switching as against the actual work,
Yes.
useful work, I would say. Okay, I
Yes.
see. I see. Yeah. Thank you.
Mm, mm. Okay. So these are some of the results, which is so here, as you can see, um, So what do you observe here? If we compare the versions using
Hmm.
busy waiting and the version using metasis, we don't see much difference in the overall runtime when the programs are run with very fewer threads than the codes. Okay, this is not surprising because each thread only enters the critical section once. Unless the critical section is very long or the pthread functions are very slow, we wouldn't expect the threads to be delayed very much by waiting to enter the critical section. However, if we start increasing the number of threads beyond the number of cores, the performance of the versions that uses mutexes remains largely unchanged, but the performance of the busy waiting version gets degraded. And that's because
Wait time.
if there are more threads than cores, this should make sense because as we have just discussed, we have like in case let's say we have two cores and 5 threads, then thread 0 will be in the critical section, thread 1 will be in the busy loop, thread 2 and 3, 4 will be rescheduled by the operating system. And after thread 0 completes the critical section and sets the flag to 1, it will be terminated and thread 1 can enter the critical section. Right?
Yeah, here, ma'am, 2 4 core processors, as in we have total 8 processors independent.
Yes.
So
Yes.
till we reach eight count, the numbers
Hmm.
are almost identical. But as soon as
Yes.
we have 16, 32, and 64, the spin lock is
Hmm.
kind of getting deteriorated
Hmm. Hmm.
much more than
Hmm.
mutex is remaining stable even there. Yeah,
Yes.
yeah, this is a very good slide.
Okay.
So
So
that's the reason we need to be, as in when we are programming, particularly in a
yeah,
parallel way, we need to be very clear about what kind of systems which we are going to deal with and
very
what to
important.
use when, what to use
Yes.
when. Busy wait is going to be almost identical till we hit the
Yes.
boundary, eat.
Hmm.
But after that, it is going to hurt us big time.
Yes.
Yeah, makes sense.
Okay. So yes. So with this, uh, you all, I'll upload the code for the you know all the pthread codes, including the ones we discussed in the last class, and some of the changes that I did post the class. Uh, I'll upload them today, and then you all can then now play around with pthreads and uh, and try these things for yourself, like what we just saw. You can create a table for yourself similarly, and see the difference in execution time as the number of codes increase. Okay, so moving on.
Should we take
Now,
a short break? Should we take a short
yeah,
break
yeah,
since
it
we are
should,
at
yes,
logical
sure,
point?
sure. Yes, I understand. Yeah, so maybe we'll meet in another 10 minutes is fine,
5 minutes should
or
suffice.
five.
Five
Okay,
minutes should
okay, okay, fine,
suffice.
fine. So we'll meet at 9:50.
Yeah, thanks.
Thank you. Okay, so should we begin? Yeah.
Yes, ma'am.
So
Yes, ma'am.
yeah. Okay. So we'll start our discussion with OpenMP. Let's see how much we are able to cover. But anyways, my next plan is also to, you know, uh, do some kind of do these different problems with OpenMP, MPI, and Pthreads so that we appreciate the difference and understand the three programming models before the midsem so that you're prepared. Uh, so we'll start with OpenMP. Let's see how many functions what we are able to cover. So OpenMP, similar to pthreads, is a shared memory programming model. That means our threads can communicate through shared variables or memory. So we do not have to worry about the explicit communication that we had to take care of in MPI. Okay. So this makes things quite simple when we are working with multi-threaded programs such as C, C++, and OpenMP is available to you in C, C++, and Fortran. Uh, what we will be using in this code will involve using C programming language. Okay. So even if there are any questions asked in the midsem with respect to the OpenMP or MPI, they will be basically by you with using C, and which will involve you providing a solution to the question based on the whatever the context using some OpenMP functions or pragmas, or at least trying to what we expect you to at least understand a programming model and develop a solution which can use that programming model in order to perform the expected operation. There might be some simple syntax issues that you might have, you know, kind of end up doing because you are not very used to C programming, or you're not very used to, you know, uh, not hands-on with the C with C, but that's fine as long as you are able to uh, provide the solution using the the programming model that you are asked to, and whatever specifics that are needed for making it, for parallelizing it, and maybe to ensure some whatever, if there is any critical section, how you take care of it, but the what you use for it, those things will be considered while grading. Okay. So the clarity in using these models for the particular task is important from this from mid-sem perspective, and not exactly very specifically the syntax. Okay. So yeah, moving on. For OpenMP, as I mentioned, you can use it with C, C++, and Fortran, and we'll be using C. Uh, GCC will support OpenMP, so as long as you're using a WSL with GCC, that should suffice, and you should be able to start working with OpenMP right away. So how OpenMP works is you have a master thread which will start, and then you can have some multiple parallel regions in your code. So you can have multiple parallel regions in your code, then followed by some serial region, then parallel region, some serial region. And these multiple parallel regions might be spawned with different number of threads. The first region could use 3 threads, the second could use 4, and third could use 2. And that's allowed. So and this forking and joining is taken care of by OpenMP. That headache or that overhead you do not have. What we experience in pthread. Pthread is more efforts in terms of parallelizing the code because we are working at the thread level. You're doing the assigning the task at thread level, whereas OpenMP makes your life much easier compared to pthreads, and we'll see how that is done. So let's start with the classic hello world program. If you want to convert your serial code to a parallel OpenMP code, you need two things. First is a header file, which is omp.h, which is must, and whatever code in your simple C program you want to parallelize, that should be inside a hash pragma omp parallel. Okay, so inside this function, whatever you write will get parallelized with your OpenMP. And how do you execute this? Is the GCC minus F OpenMP and your program.c. If you want some special executable name, you can mention it. If you do not mention it, it will create a e.out. Okay, but what is important is dash F OpenMP, which is a flag which tells your compiler that it is OpenMP code and you have to compile it. So let us just run this hello world program so that we see how it looks.
Ma'am, we'll be only using
Yeah.
C language, right? Not even C++, right?
Yeah,
For
yeah, we
opening.
will stick to C. That's fine.
Okay.
Okay, so let's see the hello world program. Let's run it. Okay. If you do not mention the number of threads, that is, you if you is this visible or do I have to zoom it?
Can you zoom it, man?
Better?
It's better.
Hmm? Okay. So here first is we have not mentioned the number of threads and we are saying hello world. Okay. So let's compile this code. You have to provide the flag. How many threads are executing this? 8, right?
Yes.
Hmm? Now let's mention the number of threads. I think this was saved before. So now 12 threads have executed it. If you want to know which thread is executing what, the function is omp get thread number. Okay, omp underscore get underscore thread underscore num gives you the number of your thread that is executing in open. Okay, so let's compile this again. As you can see, the order of threads is not in our control, or that is what system decides when what will execute, and the number of threads we can specify. Okay, here is a simple hello world OMP code clear or any doubts here?
What, like, ma'am, in MPI, there is an option like oversubscribed. If numbers of thread is more than the numbers of core available on the systems, uh,
Mhm.
we always get some error. Here we are not getting. You are giving 12. If you will give 30, that's are we going to get something like that? It's we don't have that many cores available on the system.
It is for OpenMP. I did not get this such error before. The one you're mentioning, we can try with 30 as well. So
It's
it's
working
not
here.
happening. Yeah.
But in MPI, like if I have a 4
Hmm.
cores on my machine and I'm running with 8 threads,
Mhm.
I used to get
Mhm.
that you are oversubscribing. Means we need to give the oversubscribing option so that it will use the same code for multiple runs. MPI, I'm talking about.
Okay. 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 I'm sorry, but I have not uh, come across this issue, but I'll check and I'll let you know if there is any uh, specific cap for OpenMP.
Yeah. Yeah.
So okay, so let's continue. Other than that, I hope the Hello World program is clear. So let's move on with,
Ma'am, one more question. By writing and by seeing this code for this pragma line in the
Hmm.
threads, we have to write many line of the code to handle that. Is there any particular scenario when we should go for the P thread or open MP?
Yes. So yeah. So yes, as I mentioned, and with P threads, no, you get the thread level granularity. Like, if you want control in terms of like fine grade control, like when you create the threads, when you join them, when you detach them, if you need such control or any low level threading operations that you need to do, then you should use P threads. Or if you also, if in case if you need like direct control over thread synchronization for some reason,
Mhm.
also P-threads are used for Unix-like system, na? So that
Yeah.
is also where you decide whether you need P-thread works or OpenMP works. OpenMP is best for, especially for parallelizing the loops. If you want to observe speed up in a minute, in few minutes for us for any code, OpenMP is gives you that with very few lines of code. Like a hash break OMP parallel for can do wonders for loops. Okay, so the focus is more on data parallelism, basically matrix operations, scientific computations, and
Okay.
yeah, and OpenMP is supported by many compilers. So that is also advantage kind of with when it comes to OpenMP. So especially, so the difference would be that yes, level of control. P-threads gives you fine grade, whereas OpenMP is a bit of high level, less control. Uh, Complexity, P-threads require manual thread management, a lot of more, difficulty or challenging, or you need that expertise in using with P-threads. But OpenMP gives you these compiler directives which are very easy to use. The other thing will be the obviously the portability. POSIX specific, it will not work on non-POSIX systems. And OpenMP is portable across many platforms because OpenMP supports a lot of platforms. And yeah, so and the last difference will be obviously the use case. You get the P-threads, you do custom threading logic, in especially something like real-time systems is where P-threads will be really useful. OpenMP is more for data parallelism, scientific computing kind of scenarios where you can, with few lines of code, you are able to gain a great performance change.
Okay.
Okay,
Okay.
I hope
Yeah.
this will
Yeah.
be clear.
Maybe in addition to that, one more difference I can
Yeah,
notice.
please. Yep.
LP,
Yes.
a P-thread is coming by default with the compiler, and for OpenMP, we need to install the different library to make use
Hmm.
of this.
Yeah. That yes, that is also one difference. But hmm. Anyone else can think of from whatever you've observed so far?
This is like same code running across threads. So I hope there will be some example where I mean we have different threads and having different code.
Hmm. Yeah, that's a good observation. So, can we get anything early thread level granularity? How can we do that? So, we'll see some examples where you can divide the work into different threads. That can be done. Yeah, but not the level at which you can get to pthreads, that level of granularity you may not be able to see in OpenMP. But we can have this discussion again once we go through all the options that we have in OpenMP, what you think about both. Okay. Moving on, we've seen the Hello World program. Uh, the OpenMP memory model is a shared memory model, as we mentioned. Threads shared memory, they communicate through memory as well as they have their own private memory as well. Okay? So threads can have some private variables which are, I'm sorry, specific to them and are not available to other threads. Now, how do you declare this, or how do you understand what are private and what are shared variables? So for that, you have these different levels of visibility. Where private is a variable list which is private to each thread. Shared is shared and is visible to all threads. You have something called as first private and last private. So first private is similar to private, but this M here. Okay, so here, I need a file. So L is 10, M is 11. So value of M here is 11 for each thread when it begins. Okay, the private variables K and L both are private and will be equal to 0. But M here will have the value of 11. So this specifies that each element will have a variable and that variable should be initialized with the value of the variable which exists before the parallel construct. Is it clear what these three are?
This one, can you explain one more time? The first private,
Yeah.
not getting.
Yeah. Okay. So all threads will have their own M. Okay. Let's say 10 threads are there and each thread will have their own M. But this M will get initialized to 11 because it was initialized to 11 before the pragma. Okay. If you call it first private. If you do not call it first private and it remains private, that means the value that it will have, if the same M was private, it would have the value 0 because that's a private copy of that thread, private variable of that thread. Is it clear? So
Yeah,
each
just to add
thread,
up. Yeah, just to
yeah,
add up to ma'am's point, if you see in this particular snippet, L is equal to 10 and M is equal to 11 before we enter into parallel block. In the parallel block, we say K and L are private variables. So every thread will get its own copy of K and L. First private M, again, every thread will get a copy of M as well. But important distinction is when we say first private, and if you see the value of M before entering into parallel block, it is 11. So every thread will get a copy of M and that value, initial value of M would be 11 for each thread. Well, if you consider L, which is similar before entering into parallel block, it has value 10. Despite of that, it will get initialized to 0 in every thread's memory. As in, if you can come on the earlier slide, ma'am. Here we could clearly see that every thread has its own private memory. So whenever we say any variable is private, then only that particular thread is going to see that variable. So every thread will have its own private quota of memory wherein private variables will be added. And by default, all the global variables are going to be shared across threads. The example which we saw on the next slide, can you please come on next slide, ma'am? Yeah. Variable L and M, both of them are private variables by virtue of which every thread will have its own copy. Difference between the first private and private is the initialization value. As in L is going to be initialized to 0 just because we said it is a private variable only. So by default, it will get initialized to 0. Well, when we say first private, M, M's current value, which is 11 in this particular context, will be persisted, as in m's value will be noted, and every thread will get m copy with value as 11. That's the only difference. Does that help?
I hope this is clarified. Okay,
Ideally,
let's.
it
Ma'am,
is
how
like
about
If not,
any.
let's just see an example. Let me just.
ma'am, how about shared variables? Would they get initialized to some value, or they being
Yeah.
shared
So
whatever value they had, it will remain?
yeah. So here, yeah. Let's run this so that I think it will clarify better. So here, shared variable is 10. First private is 20. First private is 30. Okay. So before parallel region, these are the values. Inside the parallel region, these are the values. So let us just compile this. Uh, Sorry.
And there is a variable called shared also here in the code. Shared where.
Yes, this is a shared variable,
Just like a
and that
private,
is
first private, there is a shared keyword.
that is shared. Yes, shared is shared amongst all the threads.
It's a kind of a global variable we are making.
Yes, yes. So, before parallel region, the shared variable was 10, private variable was 20, first private was 30. Okay. Now, inside the parallel region, each thread will take the shared variable. It will take the private variable. It will increment its first private variable. Okay, based on what is the I value. Okay, and it will print what is the shared variable and what is the private variable and what is the first private variable. So before parallel region, the shared variable was 10, private was 20, and first private was 30. Inside parallel region, shared variable, now this is thread 2. So shared variable was 10, it remains 10. We have not done any changes to it. We should have maybe. I'll just update it. Sorry. I think that's otherwise. I'll increment that also. I create some issues, but it's okay. Okay. So before parallel region, shared variable was 10, private was 20, first private was 30. Now inside parallel region, thread 1 had shared variable to be 11. It updated it. Private variable became 1 because the private variable was reinitialized and its copy has the value of I. Since thread is 1, private variable is 1. The first private variable was initialized to 30, but now we have updated it plus I, so it became 31. Similarly for thread 0, in thread 3, you can see that since the shared variable was 10, this also made it 30. After parallel region, you can see the shared variable value is garbage now because multiple threads have worked on it, added the value, and ended up increasing the value, which is not reflected by any of them in the parallel region. Private variable is what the value was before because this value is not same as this value because this is private variable which is outside the scope of the parallel threads, and this is in scope of each thread, so this value is not reflected here. First private remains what it was, but inside it it was initialized and each thread is had its own copy of first private variable and they updated it themselves. Is this clear now? Is this example good enough for you to understand what happens?
Total, how many threads we specified initially?
Or we can change it. No, we have not. Okay, since we are doing it for four loops, I think only four threads executed it. But if you want, we can mention the number of threads here. So
So the for loop was for how moments? How many iteration? Four only?
yeah, four only.
Ma'am,
Okay. So by
if you are
default,
not
it's
if you are not
Sorry,
specifying
sorry,
it,
sorry. Because I'm sorry. I realized it that we have used the OpenMP parallel for. That's why it is. We have not mentioned number of
okay.
threads.
Okay,
But yes,
got it.
yeah. So it parallelizes the for loop and gives one thread each one loop count to each thread, something like that. So it divides the loop automatically into threads
ma'am,
based on what is the requirement.
uh,
Yeah.
can you specify some numbers of threads? What
Okay.
I'm
You want me
thinking,
to?
if what I'm thinking, if we are not giving any value, it's taking by default the numbers of cores available and doing the parallelism.
No. If that was the case, it was would have taken 8 that we saw in the hello world without mentioning.
Yours machine
Here
had
it is.
8.
Yeah. But here it is 4 because there are 4 loops and 4 loops are divided into 4 threads by parallel
Okay,
for.
okay,
But
okay.
okay, let's mention. I'll mention number of threads as 12 here, and let's see what kind of results we see.
Yeah, it's 4. It's doing the parallel of loop count.
It's yeah. This is not having more threads makes no sense here. So it is
And
not
here,
adding threads.
ma'am, shared variable is something like it's a kind of we need to handle it using the some locking mechanism because we are sharing this variable. That's why
Yeah.
we
So
are
here we'll
seeing
need some critical section.
yes random variable value in that.
Yeah. So there is option since it's a single variable. There is option in OpenMP atomic. So I'll just add that.
No.
So now although it's added by you know each uh, thread added it, this value now will remain consistent because how many threads? 4 threads, right? So each one will add 1 plus 3 plus 3, 6. This became 24. Now this is critical actually. Yeah. So there is also another option of using critical.
Ma'am, what does atomic do?
Yeah.
The one which we used
Atomic
just
atomic is for only one thread at a time, which allows only one thread at a time to do the change.
okay, but then in that case, shared variable should have been earlier value plus 4. So 14 maybe.
Yeah, it didn't work. I think it didn't work here.
Yeah, so that's what I'm wondering why it didn't work here. This is only one. Now I think I should do atomic capture here
Yes.
because atomic is only for one instruction because we're doing shared is equal to shared plus I, na? So this
One.
Okay, I'll use critical for now. We can read.
Still.
Value is shared variable is 10. Each one will. This also allows critical access to each thread. So it is adding the value of I. So it became 24.
Can you run it
Sorry,
one
I
more
have. Sorry,
Ma'am,
sorry.
I think it
I
has
have.
to be on same line.
Sorry, I have also done this somewhere in the code. I missed it. I'm sorry. I had added the atomic part, the later part. I have, which I loop. Okay, for loop. Okay, this is fine now. This is fine, right? Hmm?
Why, like it should be a final value 11 plus 4. 10 plus 4, 14 should
No,
be final. Why it's a
no.
16?
The thread number gets added, na?
Okay. Okay.
It's the thread number.
I is the third number.
Ma'am,
Yeah, I
what's the
said
difference between private var and first private var and only initialization part? That private is
yes. Only
uninitialized.
initialization. Only
Okay.
initialization. Yes.
And how the syntax differs?
So here you have to mention first private and whatever is the variable, and
Okay,
private, and inside that whatever the variable is. It could be A,
got it.
B, C, D, L, M, whatever. First private and private is the only difference in terms of the function which
Initialized.
specifies
Oh,
initial values. Even now, if atomic works, that means that the atomic does not need this. Yes.
Yeah.
Hmm.
Why it didn't work
Okay.
earlier and now it is working? I'm lost.
No. I no. What happened is I had added a few lines of atomic towards the end for shared variable, which I missed considering, which I now removed. I had added atomic part somewhere. So I did not notice that earlier. Then when I removed, so we were trying to update twice. That's why it was giving us 24. 6 plus 6.
Okay, what was the
So
earlier code and
this
what is new code as in?
no there this was done twice in the function.
Yes.
Okay, it was done twice in the function. Okay, that's the
Yes.
reason.
Hmm.
Oh, I see. I
Yeah,
see. Okay.
yeah.
Okay.
And I had
Okay.
not
So
noticed that I
16
have done it too late.
plus,
Hmm.
okay,
Yes.
16
So
and
10
then
plus 6
20.
plus plus 6.
Yeah, can you
10
put
plus
that?
6 plus 6.
Okay, 10 plus 6 plus 6. It would be 22, right? We were seeing
Oh,
value
sorry,
of
24.
24. Can
Yes,
you just
yes.
copy paste that block one more time and let's see? Yeah, let's compile and run and see if that's the case now. We expect 22 to be here, right?
So no,
Okay.
I had put one more outside. Something like that was there in the code. I see something like this was there. Now I don't remember what I removed that part.
That's okay, ma'am.
So
Okay, okay.
yeah.
I,
So okay, if I execute this again, I might get get 24. Something like this was there.
There was
Okay.
some random means we
One more statement,
process.
random of updating, or maybe I was updating with to something. I don't know. This will
Okay. So any
something like that was
unintentional
there.
modification was shared variable was there. So
I'll check. I'll check if I have one this version before somewhere. I'll check. Uh,
Ma'am, this
there's
atomic,
something
can you
more.
atomic one, can you repeat?
Yeah. So yes, let me go to the slide so that okay. So yeah, before moving on to atomic, uh, um, okay, I'll just talk about atomic then because there are a lot many other things that I will talk. So atomic are meant for doing atomic operations on shared variables. That is doing only one single indivisible operation and ensuring that there are no databases among threads. Okay. So if
Okay,
there is
okay.
any, you are trying to update some shared data, okay, that you can put in atomic. Okay. There is another option. So this is something like this, where whatever shared variable is there, you put a hash pragma OMP atomic and shared variable plus plus. This will be incremented by only one thread at a time. Okay. We have another option, which is critical section, which is here also you put uh, statements inside this hash pragma OMP critical, and whatever code is put will be executed by one thread at a time. But critical section is meant for a block of code, okay, and uh, not a single thread, single line of code. So something like this. These are two lines, but you can have more lines here. Now, in terms of if there is critical section and why do you need atomic? Any guesses like why you need atomic if you already have a critical section? Any guesses?
To isolate it,
Hmm?
to
No, it's
isolate that section.
it's a similar you just talk about in the previous sections. If we are just changing one variable, we should go for the flag locking mechanism, flag kind of locking mechanism that's more efficient than the critical section.
Uh,
I
okay,
think you already
maybe,
answered
but
them, right? So,
I'm asking between atomic and critical section. Okay, we have two options, right? And both are doing the same task. Only thing is atomic is doing only for one instruction, right? Why have a separate, pragma function for only doing it for a single instruction when you have a operation which is like which can do single as well as multiple?
yeah, since it is kind of a directive, right? Pragma OMP critical might be considering, or it would be a heavy operation as against the atomic, because atomic knows that I just have one instruction. So whatever needs to be executed as the next statement, that needs to be done in an atomic way, while critical needs to worry about entire block of data. So probably the code which gets inserted by compiler would be heavy in case of critical section and lighter in case of atomic. That could be a possible distinction.
Yes, yes, yes. You are on the right path, and I'll leave it to y'all. You all post this session, go and find out why we need atomic. You are on the right path, but still there are a few other interesting aspects why atomic help us, make the code much faster compared to critical. And I would like to learn from you all whether you found the reason interesting as well. Okay.
Okay.
Yeah. And so in the next class, we'll continue our discussion with OpenMP, and we will also try to write a few codes in OpenMP as well as MPI, compare the two in terms of how the implementation is for both the programming models. Hmm?
Okay.
Ma'am, one more question. This is the next
Yes.
class is the last class before the midsum.
Hmm.
So in the midsem, we are just going to get like OpenMP, pthread, and MPI.
Yes, OpenMP, pthread, MPI, and some questions on performance analysis.
Okay. Okay.
Okay.
Okay, at high level, if you can explain what kind of questions we can expect, as in last time we spoke, right? There were three questions only.
Yeah, yeah.
So if you
So
can just at a
yes.
high level would help
So
us to kind of prepare well.
yeah. So yes. So there might be a question on writing a small code on one of these programming models using some technique that you need for that particular application. Where as I mentioned, syntax is important in terms of understanding what you're exactly doing, but it's not critical. Okay. Uh, the There would be some direct questions in terms of functionality of some of the like techniques that you use here. Then there will be some questions on doing some performance analysis in a particular scenario of execution of any code and so and a few yeah. So such questions will be asked because it's a closed book exam. So considering that, whatever could be answered with whatever you have learned so far, you will be asked.
Okay.
Okay.
Okay. And do upload
Okay.
last year's
Yeah.
recording, last class recording, this class recording, as well as the PPT.
Sure. The
So that
recording is directly uploaded on the Teams, right? So
I wasn't able to see that for last class at least.
is it? Okay.
Let me
Let me
check.
check.
Yeah, did I miss something?
PPTs I have uploaded even the last class. I'll upload the code. I did not upload the pthread codes. That I'll upload now.
Okay, August 29. It is there. Sorry. I think I missed it.
And OpenMP also I'll upload all the codes, or even what will cover in the next class. I'll upload, and if you have time, you can go through them now, and we'll continue our discussion in the next class. Mhm.
Okay.
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 Yes.
Okay.
Okay.
Yeah. Thank you.
Thank you, ma'am. Thank you.
Yeah.
Thank
Thank
you.
you.
Thank you, ma'am.
Thanks, ma'am.
Thank you.